One equation. And told you it could explain everything. Not just why apples fall. But why stars shine. Why atoms exist. Why time flows. And what happened before the Big Bang. Would you believe it? Because Albert Einstein spent the last part of his life chasing exactly that. And he died without finding it. On April 18, 1955, newspapers around the world announced his death. Many of them showed a photo of his desk. An open notebook. Pages filled with symbols. He was working on a unified field theory. A so-called theory of everything. The dream is simple to state. One framework. One set of equations. That unifies the four fundamental forces. Gravity. Electromagnetism. The strong nuclear force. And the weak nuclear force. Einstein believed the universe is not a patchwork. He believed it has a hidden unity. In private letters, he also admitted something else. Doubt. He wrote that from up close, things looked different. He said he was not sure any concept would stay unshaken. He even doubted whether he was on the right path. And yet he kept going. Because the prize is enormous. A final theory would not just be more knowledge. It would be the source code of reality. And history shows that when physics unifies, civilization changes. So let's trace this story. Not as a museum tour. But as one long chase for a single idea. Unification. Long before modern science, humans tried to simplify the world. Ancient thinkers asked a basic question. Is nature made of many unrelated things? Or of one underlying pattern? Some Greeks said everything is built from four elements. Earth. Air. Fire. Water. It was elegant. But it failed to explain complexity. Another Greek, Democritus, proposed a bold alternative. Everything is made of tiny indivisible pieces. Atoms. Too small to see. Too small to touch. Critics said it was unprovable. But Democritus argued with indirect reasoning. Even today, indirect evidence drives science. We infer the sun's chemistry from its light. We infer DNA structure from diffraction patterns. We infer the universe's age from cosmic signals. Then came a second kind of unification. Not matter. But law. Pythagoras looked at music. And saw mathematics. He noticed harmony comes from simple ratios. So he asked a dangerous question. What if nature itself is written in math? What if the world obeys one mathematical order? Centuries later, this idea exploded. In the 17th century, scientists attacked the sky with numbers. Johannes Kepler described planetary motion with mathematical laws. Galileo pushed experimental science. He used a telescope to see what doctrine said was impossible. Mountains on the moon. Phases of Venus. Moons orbiting Jupiter. Nature was not obeying human tradition. It was obeying something deeper. Then came Isaac Newton. Newton unified heaven and earth. He claimed the same law that drops an apple also steers the moon. Gravity. He built laws of motion. And a law of universal gravitation. With those equations, you could compute trajectories. Predict comets. Design bridges. Aim cannons. Centuries later, engineers still use Newton to guide spacecraft. Newton's unification was so powerful that it looked final. For a moment, it felt like physics was basically done. But then a second pillar rose. Electricity and magnetism. At first they looked unrelated. Electricity shocked. Magnetism pulled. Michael Faraday revealed their connection. Move a magnet through a coil. You get current. Change magnetism. You create electricity. He introduced a radical concept. Fields. Not just forces at a distance. But something filling space. James Clerk Maxwell turned Faraday's insight into equations. Maxwell unified electricity and magnetism into one system. Electromagnetism. Then Maxwell did something stunning. His equations predicted waves. Waves made of oscillating electric and magnetic fields. He calculated their speed. It matched the speed of light. So light is an electromagnetic wave. This was another unification. Light became part of electromagnetism. And with Newton plus Maxwell, physics again looked complete. In the late 1800s, some even spoke about the end of science. They were wrong. Because Newton and Maxwell did not fit together. Newton's world assumed absolute space and absolute time. Maxwell's equations implied a constant speed of light. And those two ideas clash. If speeds add, light should look faster from a moving train. But Maxwell says it does not. That contradiction sat in the foundations like a time bomb. And the key came from a teenager. Albert Einstein. Einstein asked a simple question. What would it look like to chase a beam of light? If you could run alongside it, would you see a frozen wave? Maxwell's equations did not allow that. So Einstein made a shocking choice. He kept Maxwell. And changed our ideas of space and time. Special relativity was born. Time is not universal. It depends on motion. Clocks on fast ships tick differently than clocks at rest. Length can contract. Energy and mass are linked. E equals mc squared. That equation is not a slogan. It is a conversion rule. Mass is stored energy. Energy behaves like mass. This helps explain why the sun shines. In fusion, a tiny amount of mass becomes energy. Relativity also changed gravity. Newton's gravity acts instantly in its simplest form. But relativity demands no influence, travels faster than light. Einstein rebuilt gravity from scratch. He began with a strange feeling. Weightlessness. In free fall, gravity seems to disappear locally. This became the equivalence principle. Acceleration and gravity are locally indistinguishable. Then came the leap. Gravity is not a force in the old sense. Gravity is geometry. Mass and energy curve space-time. Objects follow the straightest paths they can, which look like curved orbits to us. Light bends near mass because space-time is curved. That predicts gravitational lensing. Planets precess. Mercury's orbit shifts in just the way Einstein's equations demand. So Einstein unified space and time. And he redefined gravity. Now he wanted the next step. A single theory that unifies everything. But while Einstein was bending space-time, another revolution was rising. The quantum revolution. It began with a nightmare in classical physics. Why do hot objects glow with a specific spectrum? Classical theory predicted an absurd result. Infinite energy at high frequencies. Max Planck solved it by desperation. He assumed energy comes in discrete packets. Quanta. That was not a small tweak. It was a new kind of reality. Einstein pushed it further. He applied quanta to light itself. Light is not only a wave. It also comes in particles. Photons. So light has a dual nature. Then the question expanded. If waves can act like particles, can particles act like waves? Yes. Electrons produce interference. Even when fired one by one. The double-slit experiment became the icon. The pattern suggests a probability wave. Not a tiny billiard ball. Erwin Schrödinger wrote an equation for these waves. Paul Dirac then tried to merge quantum theory with relativity. He succeeded in a way that shocked everyone. His equation implied electron spin. And it implied antimatter. If the equations are symmetric, nature may contain opposites. The positron was later discovered. Antimatter was real. At this point, a theme becomes obvious. Symmetry. Physicists often call symmetry beauty. Not because it looks pretty, but because it constrains reality. A symmetric theory has fewer arbitrary parts. And symmetry can predict new phenomena. Spin. Antimatter. Entire families of particles. But quantum theory came with philosophical pain. What is the wave? What exactly waves? Max Born offered an answer. The wave is not matter. It is probability. It predicts the chance of finding a particle at a place. That implies uncertainty is not a bug. It is built into the world. Einstein hated this. He believed the universe should be fully lawful. He famously rejected the idea of cosmic dice. Niels Bohr defended the new quantum view. The debate became legendary. Not because of drama, but because it touched the meaning of reality. Schrödinger created a thought experiment. A cat in a box. A quantum trigger. A deadly mechanism. Before you look, the system is described as a superposition. Cat alive and cat dead. Until measurement. Interpretations differ. Collapse. Many worlds. hidden variables. But the math works. Quantum theory predicts outcomes with astonishing precision. So physics split into two towering structures. General relativity. The theory of the very large. Planets. Stars. Black holes. The Big Bang. And quantum mechanics. The theory of the very small. Atoms. Electrons. Particles. Fields. Both are correct. Both are tested. And they do not agree. This is the central tragedy. And the central opportunity. Because a theory of everything must reconcile them. Meanwhile, particle physics raced forward. Accelerators smashed matter into pieces. A particle zoo appeared. Dozens. Then hundreds. It looked like chaos. Then Murray-Gell-Mann proposed quarks. A simpler substructure. Protons and neutrons are made of quarks. Patterns emerged. The weak force explained radioactive decay. A ghost particle was proposed. The neutrino. It interacts so weakly it can pass through planets. Neutrinos were predicted. Then detected. The weak force and electromagnetism were unified into one framework. The electroweak theory. That work was recognized at the highest level. Then the modern synthesis formed. The Standard Model. It describes particles and three forces with extreme accuracy. Electromagnetism. The weak force. The strong force. It explains an enormous range of experiments. But there is a missing piece. Gravity. The Standard Model does not include gravity. And when physicists try to quantize gravity the usual way, infinities explode. The equations become meaningless. So we have two masterpieces. Relativity. And the Standard Model. They use different mathematics. Different assumptions. Different foundations. A theory of everything must contain both. And it must be finite. Not infinite nonsense. This is where the modern search begins. One leading candidate is string theory. String theory changes a simple assumption. Particles are not points. They are tiny vibrating strings. A point has no size. A string has length. And that single change can soften the violent infinities of quantum gravity. In string theory, different vibrations are different particles. Electrons are one vibration. Quarks are another. Force carriers are other vibrations. And crucially, gravity appears naturally. A graviton emerges as one vibration mode. That matters. Because gravity is not bolted on. It is built in. But the price is strange. The equations become consistent only in higher dimensions. Often 10 dimensions in superstring theory. We see 3 space dimensions. And 1 time dimension. So where are the others? The idea is compactification. Extra dimensions could be curled up into tiny shapes. So small that ordinary matter cannot probe them. Only at extreme energies would their effects become visible. Symmetry returns again. String theory strongly suggests supersymmetry. A symmetry between fermions and bosons. Fermions make matter. Bosons carry forces. Supersymmetry pairs them. Each particle would have a partner. That pairing can cancel certain quantum infinities. It can stabilize the math. It can make unification more controlled. Then the story becomes even stranger. In the 1990s, physicists found that there are not one, but several string theories. 5 main versions. That looked like failure. If nature is unique, why 5? Then a deep idea appeared. Duality. Theories that look different can describe the same physics. Like 2 maps of one city in different styles. Edward Witten argued these 5 theories are aspects of one deeper framework. M theory. In M theory, strings are not the only objects. Higher dimensional membranes appear. Brains. Different limits of M theory can look like different string theories. So the 5 may be 5 faces of one structure. Then came one of the most powerful ideas in modern theoretical physics. A surprising equivalence. One Maldacena proposed a duality between 2 very different worlds. A gravity theory in higher dimensions. And a quantum field theory without gravity in lower dimensions. This became known as ADS/CFT. The exact details are technical. But the message is enormous. Gravity and quantum fields might be 2 languages for one reality. This connects to a broader principle. The holographic principle. A hologram encodes a 3D image on a 2D surface. In black hole physics, information seems tied to the horizon. Quantum theory says information cannot be destroyed. So when something falls into a black hole, the information must go somewhere. One idea is that it is encoded on the surface area, not the volume. That hints that spacetime itself might be emergent. That what we experience as 3D could be encoded in a different way. Not as fantasy, as mathematics. So where does this leave the search? We have a clear target. Unify the four forces. And reconcile quantum mechanics with gravity. We have a strong motivation. Because unification changes technology. Newton enabled machines. Maxwell enabled the electrical world. Quantum mechanics enabled modern electronics and lasers. Relativity enabled GPS corrections and deeper cosmology. A final theory could reshape our future again. And we have a set of questions that demand it. What happened before the Big Bang? What is dark matter? What is dark energy? What is inside a black hole? Is space-time fundamental or emergent? Do higher dimensions exist? Why does the universe have the laws it has? And why do those laws feel so finely structured? Einstein chased a unified field theory with pencil and paper. He did not have the Standard Model. He did not have quarks. He did not have neutrinos. He did not have modern gauge theories. He did not have black hole thermodynamics. He did not have quantum information. He was aiming at a mountain he could not yet see. And still, the instinct behind his chase looks right. Nature keeps rewarding unification. Not every unification attempt will survive. String theory may turn out to be incomplete. Or it may be a stepping stone to something deeper. But the direction is clear. Physics is trying to merge its two masterpieces into one. To make one language that speaks both the cosmos and the atom. If that happens, it will not just answer old questions. It will create new ways to think. New tools. New technologies. And a new picture of reality. So the hunt continues. For one elegant structure. One framework. One theory. Not because we love math. But because the universe keeps hinting that underneath all complexity, there is one hidden order.